So, okay, I'm going to simplify this problem from an 8 queens problem down to a 4 queens problem for this example. But as you can see here, I have a chessboard. I'm just simply going to work off of this quadrant over here, or, all right, yeah, this 4x4 grid over here as best I can. So I've got my 4 queens here. I'm going to count my kings as queens, okay? So, but the object is to basically put these four guys in a configuration such that none of them will be able to threaten one another. It's not so bad. So this is the way my algorithm generally works. The generalized algorithm I gave you says basically for each row, what do? We are going to look at that. Sorry, for each column, we're going to for each position on the game board. Given my current position on the game board, I need to look at each choice for that position. The entire point of recursion is that we're turning these basically every decision into a local decision. Hopefully, you had the chance to watch all the videos on recursion, right? We're going to do some exercises on recursion in class, some quizzes in class on recursion. Hopefully, that should help. But the way this is going to work is that basically I'm going to look at my first column over here. Actually, I'll do it in reverse. So, because this is for you guys. So, okay. So first thing I'm going to do is that I'm going to put my I'm going to look at this first column over here. Okay? And I'm going to basically take my queen and ask, is this first spot a safe spot? Yes, it is. Okay. In that case, I'm going to try to solve the problem of putting a queen in my second column. Okay? All right? That makes sense to everybody so far? So now what I'm going to do is that I'm going to try to put my queen in this column. And I ask myself, okay, is this spot safe? I'm going to check my first spot in the column. Is this spot safe? No, it is not. Well, what about this one? No, because I'm diagonally threatened here. Well, what about this spot? That spot is safe. I'm going to go on to the next column. That's not safe, that's not safe, that's not safe, that's not safe. Right? So, none of those spots were safe. So what do? I backtrack by returning false. Because what happened is that somebody called the solve function above me. Somebody above me was calling the solve function. And since they called the solve function, that simply said, if me calling the solve function returns true, I'm going to return true because that meant that I solved the problem. But since I got a false back, I know that I hit a dead end. Okay, so this didn't work, so I'm going to go on to the next space. Is this spot safe? Yes, it is. So I'm going to call solve on the next column. And if that solve returns true, I'm going to return true because I know we got to the end. So I'm going to put my queen here. Does this work? No, that's not safe. Well, what about here? That spot is safe, so I'm going to call solve on the next column. And if that returns true, I'm going to return true because I know that it got to the end. Okay? So I put my queen here, my last queen here. Then here, that none of those two positions are safe, neither this one, neither this one. I get to the end, so I return false. This guy gets false back, so he knows that he was not able to return to the end, so he has to go and try the next position. So he tries the next position. Nope. Next one. Nope. Pull that one off. Okay? So now he'll have to try the next position, of which there's not. So he returns false. And so this first queen that we put down, it gets a return false back. So it needs to move to the next position. So it then says, okay, I'm going to solve the next column. So we take our piece and say, is this safe? Is this safe? Is this safe? No. But this last spot is, okay. Then we call solve on the next column, which goes, is this safe? Is this safe? Sorry, it's ask if this spot is safe. And it says, yes, it is. Then finally we call our last one. Is this safe? Is this safe? This is safe, though. So I'm going to call solve on the next column. And if I get true back, then I'm going to return true because that means we reached the end. Now, there is no next column, so this is our base case. There are no more choices left to make, so we return true, which makes this guy return true, which makes this guy return true, which makes which causes everyone to return true. So again, the whole entire thing here is that we're going to be solving a solution of the 8 queens problem. Not every solution, but a solution to the 8 queens problem. Does that help elucidate matters for people? So actually I found that once you understand where to put the recursion, the hardest part of the problem is basically checking for your diagonals. Checking the diagonals. Now, let me just draw this on the board. Right? Because you're like, oh, okay, I have to check to see if I'm colliding with, since queens can move in all 8 directions, I have to check 8 directions, obviously, right? But you don't. It's actually a lot easier than that. First off, we're going to be assuming that we're putting 1 queen per column, right? If we're putting 1 queen per column, you don't have to check up and down because guess what? There's not going to be anything it's the up and down. Furthermore, when I was placing my queens on this board over here, I was always placing them in this order, from the first column to the second column to the third column to the fourth column. I was always moving my queens left to right, so I never had queens in front of me in the future columns. That meant that I can cut out 3 more directions. I don't have to check in this direction, or this direction, or this direction. So in reality, I only have 3 directions for my queen to check. So I only have 3 directions for my queen to check. So that's, you have to check the upper left diagonal, the upper left diagonal going to left, and the lower left diagonal. This checking to the left to make sure if there's not a queen in that position. You want to check starting from your queen and moving out to see if there's any other queens. That's not so hard. But checking this direction and this direction, a bit more tricky. Yes?
Does the Rabbit in the Fox program have an example of how to do this without you in each direction?
Kinda. Would. But essentially what you want to do is that you want to the hardest part about this is what I suggest doing is that you use a for loop. A single for loop, because you're like, oh, I'm moving in 2 directions, I might need 2 for loops, like an I and a J. The answer is, though, that you just need 1 I because you're always moving the same amount up as you are to the left. So what you need is for int I is equal to 0, I, and then here, for your condition, what you want to check is to make sure that going this way and this way, or that going up and left, both don't lead you out of bounds. So you can have 2 conditions here. You can go and, so basically saying, hey, like row minus I is greater than 0, and column minus I greater than 0. You know, just making sure that basically you're not going out of bounds because you don't want to try to go out of bounds. Okay. Sudoku works in a very similar manner. Okay, Sudoku works in a very, very, very similar manner. So we're going to use the New York Times to just demonstrate how Sudoku works. Okay, because they have an excellent example. So Sudoku. Now, Sudoku is a Japanese game that's became kind of popular. I don't know when, sometime when I was in high school. It started appearing in the newspaper, I feel. Like, I don't remember seeing it beforehand. But essentially, the object of the game is to, if you aren't familiar with it, is everybody familiar with Sudoku, or do people need to know about it? I'm going to assume you don't know it. The object of Sudoku is that we want to fill up the board with all the numbers. It is a 9 by 9 board, and we just want to fill it, and every square must be filled with numbers from 1 to 9. But it's not as simple as me just saying, okay, I can put 1s in every square, right? Obviously, that wouldn't be much of a challenge. Now, the way Sudoku works is under very specific rules. First off, there can't be any repeats of numbers in the first, in any row. So, because there's already a 1 in this row, I can't put in a 1 in this row. See, it gives me an error. So I could put let's see. I can put a 9 here because there's no 9 in this row already. Okay? Similarly, I can't put a 1 here because also, second rule of Sudoku is that there are no repeats in the same column. Okay? No repeats in the column. The third rule of Sudoku, though, that makes this a bit tricky, is this rule over here. Notice that I try to put a 2 over here and it gives me a wrong. And this says that basically notice how it's divided into a bunch of 3 by 3 squares. There can be no repeats of any numbers in each of the 3 by 3 squares. So for example, this 3 by 3 square, if we solve it, I'll just simply do that because it's an easy puzzle and that should come up. Notice that this square is valid because it has no 3 by 3 repeats in it. Right? So those are the 3 rules of Sudoku. Actually, in checking the 3 by 3 square is the hardest part. For both to check to make sure your recursion is working, by the way, for both these problems, because that's the hardest part. That seems like it's the hardest part, but it's not. My suggestion is actually pretty straightforward. Don't worry about it being an 8 queens problem. Worry about it being an 8 rooks problem. So don't worry for 8 queens. Just check to make sure you're not having any collisions in the same row. Then add the columns in after. Then add the diagonals in afterwards. Right? That will mean that basically you can check something very easy, and if that's the case, then you should just get your problem should solve by getting a diagonal row of queens. And if you know you have a diagonal row of queens, you know you're done with the puzzle except for checking the diagonals. Similarly for Sudoku, I would just simply test to make sure do the rows and columns have no repeats in them at first. And then add the 3 by 3 square, which will tell you how to solve. So how do we solve Sudoku? Okay, well, this game is one of masterful logic, right? You're supposed to use logic and process of elimination and deduction and induction to figure out this puzzle. Or you can solve it like a computer solves it, which is that I'm just going to randomly hit things until I get a number that works. Well, not randomly. I'm going to go forward and basically move my hand along the keyboard until I get a number that works, right? If I get and the way it works is that if I get to a number that's already filled, I just simply go on to the next number. So I get to the end of a row, and I move to the next column and set my row equal to 0. That's the way that algorithm will work. Okay, and I just keep doing the same. And if I hit a dead end, I just simply erase my square and back up. Right, and because this is actually considered to be an easy puzzle, I'm not going to have much in the way of backing up to do. Right, it is actually kind of sad that this is the way all you have to do is just simply go left to right like this. But that is Sudoku for you. It's actually, although actually it is an NP complete, that if it's generalized out, it's actually an NP complete problem. It is a problem that the answer is relatively hard to solve, but checking the answer is actually monumentally easier. And so we just simply go that way until we are out of bounds on the last row. All right. So the easiest way to check your 3 by 3 square is to use division and modular arithmetic, and that is my hint. The idea to check your 3 by 3 square, the easiest way is to figure out what the top left corner of the square you want to check is. So how do I know that basically I can't put a 1 right here? Well, the first thing I'm going to do is I'm going to go to the top left square over here. I'm going to figure out what the top left portion of my square is for this 3x3. And I'll just simply go through and check each of these things to see, hey, is there a 1 already here? Or is there a 2 already here in my 3x3? Now, how do I do that? How do I figure it out? So once you figure out the top left of your particular 3x3, it actually becomes a lot easier. How do I do that? The answer is that if I take this and divide by 3, it'll give me actually like the coordinate of this. Actually, I don't need to use modulus. If I just simply divide by 3, like my row column coordinate by 3, it will give me which of these giant squares I'm in. And then I can just multiply by 3 to basically translate it back to get the top left of that giant square's top left corner. So it actually becomes a lot easier if you do it like that. All right. So the recursion is actually fairly. Recursion is an immensely powerful tool, and it is one you should definitely learn, because when we go over trees, which will, and I have to chart out the rest of the semester. I'm not sure if we're going to go over trees on Monday, or if I'm going to leave Monday to do work, but probably that's going to be left for Monday. We'll probably work on this more Monday, but trees basically work solely off recursion. All right. That's what I got for you.